For lesson 10, we're going to get away from calculating volume for a little bit, and we're going to talk a little bit about a specific principle that applies to comparing volumes between shapes. So it's called Cavalieri's principle. Triangular prism T and rectangular prism R are shown in the diagram below. A cross-section of each prism is shown at 3 units above and parallel to the base. So they want us to find the area of T prime and R prime. So basically they want us to find the area of the two cross sections. So the first one is a triangle. So area of a triangle is 1/2 base times height. Well, the cross section, because a prism is congruent to its base, so if we look up at the top, we've got 1/2 10 times 3.3, which gives us an area of 1/2 times 10 times 3.3, gives us an area of 16.5. So if we go over here to the rectangular prism, we have a volume, or excuse me, an area of just base times height. So our base and our height, 4 and 4.125. And that also gives us an area of 16.5. So although those two cross sections have a different shape, they are technically the same size. Now we want to find the volume. Well, we know our volume is really capital B times H for both of them, because they're prisms. So we already found the capital B in each. And if you look, each prism has a height of 5. So if we take the 16.5 and multiply it by 5, we get 82.5. Same thing over here. We take the 16.5, that was the area of the base, multiply it by the height of the prism, and that gives us 82.5. So now, the total heights of the prisms were 5, but the heights of the cross sections off the bottom were 3 and 3. If a height other than 3 was chosen for the cross section, would the cross sectional area be this of either solid change? So like if we took this rectangular cross section and moved it to only 2 units off the bottom, and if we move this triangle up, so maybe it was 4 units off the bottom, would their size change? And the answer to that question is no. In prisms, cross sections are congruent everywhere. So it doesn't matter where that cross section is drawn in that prism, as long as it's parallel to the base, those are all going to be congruent. So here's what Cavalieri's principle actually states. Two objects with the same height and the same cross-sectional areas will have the same volumes. So you can see here, you've got 3 different what appear to be prisms. One's right, one's oblique, one's a little bit curved, but technically the bases are still parallel to each other. Both bases are rectangles, A times B, and they both have a height of H. So since these 3 have the same cross-section areas and they have the same heights, all 3 of those shapes are going to have the same volume. And here are some other illustrations. You have a pyramid, or 2 different pyramids, I should say. As long as their cross-section areas are the same, then their heights are the same, the volumes are going to be the same. Same thing here with the steps. You can see they basically just took all the steps and slid them over to one side. But if those cross-sections at each level have the same area and the same number of steps going up, then their volumes would be the same. So here's probably the most standard Cavalieri's principle question. So given 2 stacks of quarters as pictured in the figure below, what do we know about their volumes? So if we look at them, they both have the same height. They're both a stack of 1, 2, 3, 4, 5, 6, 7 quarters. And they both have, and all quarters are the same exact size. So since all quarters are the same size, so in our Cavalieri's principle question, that's acting as our congruent cross sections. And the stacks both have 7/4. That's acting as our equal height. By Cavalieri's, and I'm not going to lie, I never remember how to spell it. Cavalieri. I think that's how you spell it. I'm just going to shorten it probably for the rest of the lesson. By Cavalieri's principle, the volumes must be equal. All right, so that's how we can use Cavalieri's principle to apply it a little bit outside of a generic math style question. So that quarter question was a Regents question, and as is this one. A triangular prism has an isosceles right triangular base with a hypotenuse of the square root of 32 and a prism height of 15. A square prism has a height of 15 and its volume is equal to that of the triangular prism. What are the dimensions of the square base? So basically they're telling you the volumes are equal. They're telling us by them both being 15, the heights are equal. So this is almost like using Cavalieri's principle in a different direction. So therefore, the cross-section slash base, now if they're prisms, we can call them base. The cross-section or the base areas must be equal. So what we need to figure out is, we need to figure out the dimensions of this isosceles triangle. So this way we can find the area and then match that area up to the square. So because they told us this was an isosceles right triangle, we know that the two legs have to be the same. So if they gave us the hypotenuse, we can go x squared plus x squared equals the square root of 32 squared and do Pythagorean theorem. X squared plus x squared is 2x squared. Square root of 32 squared is 32. We'll divide both sides by 2, and x squared is 16. Square root both sides, and x equals 4. So we know that the dimensions of each side of that triangle is going to be 4. So now if we find the area of that triangle, 1/2 base times height, we are 1/2 4 times 4, which gives us an area of 8. So now, if we know the square has to have equal area, then the area of our square is also going to be 8. Well, the thing is, how does that help us get the length of the side? Well, we know that the area of a square is length times width, base times height, but realistically, both sides or all sides of the square are exactly the same. So another way we label it is we say s squared for side squared. So in this case, we're going to have s squared equals 8, square root both sides. 8 is not a perfect square, it does simplify. Square root 4, square root 2, and then s gives us 2 square root 2. So the length of each side of our square is going to be 2 square root 2, all right? And again, that comes off the fact that we used Cavalieri's principle in reverse, that if the volumes are equal and the heights were equal, their base areas have to be the same. So we found the missing sides of the isosceles triangle and found the area of it, and then knew that our square area had to be the same, and we worked backwards to find our missing side length. Morgan tells you that Cavalieri's principle could not be applied to the cylinders shown below because their bases are different shapes. Do you agree or disagree? Now, because one is circular and one is a polygon, it is going to be very, very challenging to get the bases or to get the base areas to be exactly the same. But the answer to this question is disagree. Because although different shapes, the bases could still have the same area. So again, although unlikely, it is possible that your circular base and your square or rectangular base could have the same exact area. So therefore, Cavalieri's principle could apply to this piece if you had that part to be true. Now, obviously, you'd have to have the heights to be the same, the heights of your cylinders, but this question is just referring to the fact that the base shapes are different. So this is similar to the quarter question we did below, or before I should say. 2 stacks of 23 quarters are each shown below. One stack forms a cylinder, but the other stack does not form a cylinder. Use Cavalieri's principle to explain why the volumes of these 2 stacks of quarters are equal. So this is also a regions question. And the reason is, since each quarter has the same base area and each stack is 23 quarters high, and again that's our equal height piece. By Cavalieri's principle, the volumes must be equal. All right, so that's really what we're going after in our Cavalieri's principle piece, is just that when you have equal base areas or equal cross-section areas and you have equal heights, then our volumes of whatever our shapes are, a lot of the times prisms and cylinders, but then our volumes of those two have to be equal.